Sulfur trioxide is an important compound in industry. Sulfur trioxide has more than one possible Lewis structure. 1. Sketch two Lewis structures for SO3, one which obeys the octet rule and one of which does not. So let's start with the first one, which obeys the octet rule. So let's count the valence electrons first. So valence electron, sulfur has 6 valence electrons, each oxygen has 6 electrons, so we have 3 oxygen atoms, so 6 times 3. So we'll have total 24 valence electrons. If I divide that with 2, we will have 12 pairs of electrons. Sulfur is the central atom. So put oxygen atoms around sulfur, connect them with a bond, distribute the remaining on the outer atoms, in this case oxygen, until they will have 8 electrons. So I'll start with first one. So 2, 4, 6, and 2, 8. 2, 4, 6, and 2, 8. 2, 4, 6. For sulfur to have 8, so I need to create a double bond between sulfur and oxygen. So this structure follows the octet rule, both for oxygen as well as for sulfur. Let's go to the next one. So does not obey the octet rule. So again, we will have 12 pairs of electrons. Sulfur will be the central atom, oxygen around. We know sulfur can expand its octet, so we can create double bond between sulfur and oxygen and distribute the remaining on oxygen. So oxygen following the octet rule, sulfur is expanding its octet. So these are the two structures. One obeys the octet rule, other doesn't obey the octet rule. Okay. State how chemists decide which Lewis structure is more stable. So chemists use a formal charge to determine which structure is more stable. The structure with a formal charge close to 0. So formal charge is closest to 0 will be the most stable structure. Formal charges closest to 0 on each atom will be the most stable on each atom. The most electronegative atoms bears negative charge in case we have to assign negative charge. Predict the length of each sulfur to oxygen bond in PM. Use section 10 of the data booklet. So section 10 is now section 11 in new specification. So all bond length will be equivalent. So the bond lengths will be equivalent. So all sulfur to oxygen bond length will be equivalent. This is because of resonance, or we call it delocalization. So delocalization. So bond length will be, if we look in table 11, bond length will be in between 143 to 161 ppm. Suggests why atmospheric sulfur trioxide is an environmental concern. So sulfur trioxide can react with water during rain and can form sulfuric acid, which can cause acid rain. Okay. So the next question is about state the name of the post-combustion method used to lower the quantity of SO3 released to the atmosphere. Okay, so we're looking for post-combustion. So the most commonly used method is flue gas desulfurization, flue gas desulfurization, in which we use compounds like calcium carbonate or calcium oxide. They neutralized sulfur oxides from the exhaust gases. So they react with sulfur dioxide. Okay, SO3 is made using the contact process. Two sulfur dioxide, they react with oxygen forming sulfur trioxide. So delta H naught is less than 0, suggests this is exothermic reaction. And x-axis we need to label as a reaction coordinate. And y-axis will be potential energy. And in exothermic reactions, reactants, they have high energy as compared to products. So our reactants are 2SO2 plus O2, and our products are 2SO3. Sketch a potential energy profile for this reaction. X is provided, label EA, and include label on the axis. So activation energy, minimum amount of energy required to start a chemical reaction. So from here to here we have activation energy, and from here to here we have delta H, which is negative. So this is a way we can get 3 marks for this question. Explain why increasing temperature increases the rate of reaction. So the reason why, particle, they will gain kinetic energy. So more particle will have energy higher than the activation energy. So more or greater proportion, greater proportion of molecules with energy greater than or equal to activation energy. That will give us 1 mark. The second mark, we need to write greater frequency of collision. Greater frequency of collision. Or we can say more collision per unit time. Vanadium pentoxide is used as a catalyst. Explain how catalyst increases the rate of reaction. So catalyst provides alternative pathway for the reaction with lower activation energy. During reaction, V2O5 changes to V2O4. Identify the oxidation state of vanadium in each compound. So in V2O5, so each oxygen is -2, so -2 times 5. So vanadium will be +5. So vanadium will be +5. Okay, Roman numeral 5. In V2O4, so each oxygen is -2 times 4, so each vanadium will be +4. So in V2O4, vanadium is +4. State the equilibrium constant expression Kc for the production of 1 mole of SO3. So capital Kc will be equal to molar concentration of products, which is SO3 in this case, divided by the molar concentration of reactant, SO2, O2, and we have a half mole of O2, so we can write down half or 0.5 on O2. Calculate the entropy change delta S naught in joule per Kelvin per mole for the production of 1 mole of SO3 gas. Use the absolute entropy values given in the table. So delta S will be equal to, delta S naught will be equal to sum of the entropies of products minus sum of the entropies of reactants. Okay, so on the product side we have SO3, and absolute entropy for SO3 is 256.8 minus, we have two reactant SO2, and absolute entropy for SO2 is 248.2, plus we have a half molecule of oxygen because they said for 1 mole, so half, and entropy of oxygen is 205.2, and if I solve all of this, that will give me minus 94.0 joule per Kelvin per mole. Let's move to the next part of the question. So outline with reference to equation why the sign for the entropy change obtained in part 6 is expected. So let's write down equation. So we have SO2 gas plus we have half oxygen gas forming SO3 gas. So we can see we have 1.5 moles of reactant gases and we have 1 mole of product. So system is moving from disorderliness to order. So this result in reduced randomness. This reduced randomness as we have 1.5 moles of gas on reactant side and 1 mole of gas on product side. Let's move to the next part of the question. So calculate the value of Gibbs free energy delta G naught of the reaction in kilojoule per mole at 773 Kelvin. Use section 1 of the data booklet. Delta H is minus 98.5 kilojoule per mole. So we know delta G naught is equal to delta H naught minus T delta S naught. So this equation is given in section 1 of the data booklet. So what we need to do, we need to convert delta S we worked out earlier on into kilojoule as well, because our delta H is in kilojoule. So let's do that. So delta H we have here, which is minus 98.5, and delta S will be equal to minus 94.0 divided by 1000. So that will be minus 0.094 kilojoule. So delta G will be equal to minus 98.5 minus temperature is 773 times by minus 0.094. Okay, let's solve this. Okay, so if I solve this, we will have minus 98.5 plus we will have 72.7, and that will give me minus 25.8 minus 25.8 kilojoule per mole. So it will be a spontaneous reaction. Calculate the value of the equilibrium constant for the formation of SO3 at 773 K. Use section 1 and 2 of the data booklet. So if we look in section 1 of the data booklet, we have delta G is equal to minus RT ln Kc. We have worked out delta G in previous question. So delta G is equal to minus 25.8 kilojoule. And we have the value of R in section 2, which is 8.31 joule per Kelvin per mole. And we have been given temperature, which is 773. Units of our gas constant are in joules per Kelvin per mole, but delta G is in kilojoules, so we need to convert delta G into joules. So delta G will be equal to minus 25,800 joules. So let's rearrange this equation for Kc. So ln Kc will be equal to minus delta G over RT. Let's substitute these values, so minus and minus 25,800 divided by 8.314 times by 773. If I solve this, that will give me 4.01. Now, so we have ln Kc is equal to 4.01. So Kc will be equal to e to the power 4.01. If I solve this, that will give me 55.4. Next part, a flask contains 0.120 mole per dm cube sulfur dioxide, 0.050 mole per dm cube oxygen, and 0.150 mole per dm cube sulfur trioxide at 773. Deduce whether the system is at equilibrium and in which direction reaction will proceed if not at equilibrium. So let's write down quotient. So quotient is equal to molar concentration of SO3 divided by molar concentration of SO2, molar concentration of O2, and half molecule of O2. So let's substitute these values. So we'll have 0.150 divided by 0.120 times by, so we have 0.050 and half of that. If we solve this, we will get 5.59. So since we can see Q is smaller than Kc, so reaction is not at equilibrium. Not at equilibrium. So reaction is not at equilibrium, and reaction will proceed to the right to reach the equilibrium. Reaction will proceed to the right to reach the equilibrium. Here's a 20.00 centimeter cube sample of weak monoprotic acid with a concentration of 0.150 mole per dm cube was titrated with a solution of sodium hydroxide, giving the pH curve shown. So it's a monoprotic, means it can give one proton away, so it's like Hx. Concentration of acid is given and volume of acid is given. So determine the concentration in mole per dm cube of sodium hydroxide using the titration acid first. So N of acid, and that will be equal to concentrations time by volume, and the concentration of acid is 0.150 and the volume is 20.00, and if I divide that with 1000 to convert that into dm cube, if I solve this I can have moles of an acid, that will be 0.00300 mole of an acid. To find out the concentration of sodium hydroxide, we know concentration is equal to moles over volume. So the molar ratio will be 1:1 because it's a monoprotic acid, and the moles of acid and moles of sodium hydroxide will be the same. So I will have 0.00300. The next we need the volume of sodium hydroxide, and we can go back to the graph and read the equivalence point. So it looks like 18 centimeter cube is the volume here. So 18 centimeter cube. So let's convert that into dm cube. So 18.00 divided by 1000. So if I solve this, I can have the concentration of sodium hydroxide, and that will be 0.167 mole per dm cube. Okay, let's move to the next part of the question. So determine the pKa of the weak acid using the graph. So at half equivalence point, we know pKa is equal to pH. Okay, so let's go back and read the graph. So the half equivalence point will be, it's 9, and if we read from there, it looks like it is around 4.8. Okay. So pKa will be 4.8. Outline why phenolphthalein can be used as an acid-base indicator. So phenolphthalein gives different colors. So phenol gives different color in acidic and alkaline solutions. So all indicators, they have one color in their undissociated form, and they have other color in their dissociated form. So phenolphthalein gives different color in acidic and alkaline solution. So in acidic solution, phenolphthalein is colorless, and in alkaline solution, it gives a pink color. So it provides a, and also at equivalence point, it provides a sharp color change. Okay. Sharp color change. Okay. Next question. Outline why phenolphthalein is suitable for this titration. Use section 22 of the data booklet. If we look in section 22 of the data booklet, so phenolphthalein has a pH range of 8.3 to 10.0. And this titration is a titration between weak acid and a strong base, and our equivalence point is greater than 7. So if we go back and look, and looks like our equivalence point is somewhere near to 9, because our equivalence point lies in between this range. So our equivalence point occurs at pH greater than 7, so around 9. So this lies within the color change range of phenolphthalein, which is 8.3 to 10.0. Okay, next question. Outline how samples of weak acid and strong acid of same concentration can be distinguished from each other. Right, there are 3 ways we can do it. So we can use a pH meter. So if we use a pH meter, pH of strong acid will be lower. So strong acid of same concentration will be lower. The other thing we can do is we can measure the conductance using conductivity meter. So the conductivity will be a lot higher for strong acid. Another thing we can do is we can add sodium carbonate, and the reaction will be more vigorous or more fizzing per unit time with strong acid. Okay, so any one of them will give you the mark. The kW of pure water is 1.00 times 10 to the power minus 14 at 25 degrees Celsius. Suggests why the kW value of pure water increases as the temperature increases. So let's write down H2O reversible sign H plus OH minus. That suggests the forward reaction is endothermic. So forward reaction is endothermic. When we increase the temperature, equilibrium shift to the right, and more water molecule dissociate and producing more H plus and OH minus. And that's why the kW value of pure water increases as the temperature increases. Number 2, calculate the pH and pOH of water at 60 degrees Celsius. Use section 23 of the data booklet. So if you look in section 23, the new value of kW at 60 is 9.55 times 10 to the power minus 14. So kW is equal to molar concentration of H plus or H3O plus ions and OH minus ions. H plus is equal to OH minus. So I can say H plus square will be equal to kW, and H plus molar concentration will be equal to square root of kW. If we take the square root of kW, H plus will be equal to square root of 9.55 times 10 to the power minus 40. If I solve this, that will give me 3.09 times 10 to the power minus 7. Now, if you take the minus log of hydrogen ion concentration, that is pH. So pH will be equal to minus log of 3.09 times 10 to the power minus 7. If I solve this, that will give me 6.51. That is a pH. So pH and then pOH. Because H plus is equal to OH minus, so pOH will be 6.51 as well. So pOH will be equal to 6.51 as well. We can't use 14 here because we are calculating at different temperature and using different value of kW. The water is still neutral and we have a new value of pH and pOH. D. 2-methyl propanoic acid and its esters are found in many foods. Predict the number of signals and the ratio of the areas under these signals in proton NMR spectrum of 2-methyl propanoic acid. So we're looking for how many different hydrogen environments there are there. So we have them 2, they are equal. So 2 methyls, they are equivalent. So I will label them as A. This one is in a different environment, so B and then C. So we have 3 protons. We have 3 different proton environment. Hence, we will expect 3 signals here. CH3, so total 6 protons, they're in the same environment, so that will be 6. And then we have 1, and then we have 1. So the ratio will be 6 to 1 to 1. Predict the splitting pattern of the signals of the hydrogen atoms on circle carbon atom into methyl propanoic acid. So we need to use N plus 1 rule. We have 1 hydrogen next door, and hence signal will split into 2. So we're expecting doublet. So peak will split into 2. So we expect doublet. Right, next part of the question, outline why tetramethylsilane TMS is often used as a reference standard in HM NMR, so proton NMR spectroscopy. So 3-4 reasons, any one you can write and give you 1 mark. So one is inert. It is inert, highly volatile, non-toxic. So any one of them will give us 1 mark. Next question. So the molar mass of 2-methyl propanoic acid is 88.12 gram per mole. Suggests why there is a small peak with M over Z value of 89. So we can see we have a small peak after the molecular ion peak. And that is because of carbon-13 isotope. So peak at 89 is because of carbon-13 isotope. Identify the fragment with M over Z 73 and 43. Use section 28 of the data booklet. So a new specification, that is 22. So we're looking for what is lost. So if I take away 88, take away 73, so that suggests me 15. So a species which has a molar mass of 15 is lost. So if I go back into the structure, so that suggests me CA3 is lost. So if CA3 is lost, then we're left with CA3, CH, COOH, and a plus charge. So positive ions, they're only detected by the mass spectrometer. The next one is M over Z 43. So that suggests me, so 88, take away 43. So 45 is lost, which is COOH. And we were left with CA3, CH plus ion. And that ion will produce a peak at 43. Predict the wave number of one absorbance other than due to carbon hydrogen in IR spectrum of 2-methyl propanic acid. Use section 26 of the data booklet, and in the new specification is section 20. So either we can write down C double bond O peak, which appears around 1700 to 1750 per centimeter, or we can write OH peak for carboxylic acid. That will appear around 2500 to 3000 per centimeter. Sorry, that should be per centimeter. 2-methyl propanic acid reacts with ethanol in the presence of concentrated sulfuric acid. Deduce the structure and empirical formula of the organic product. So carboxylic acid, when they react with alcohols, they form esters and water. Let me write down 2-methyl propanic acid here, CH3, CH3, we have H here, we have COOH, then we have, let me use a different color, so we have CH3, CH2OH. So condensation reactions, OH from an acid, H from alcohol, they react together and they form water and ester. So let me draw ester now. So we will have CH3, CH3H. So new link will develop with carbon and oxygen from alcohol, and then the rest of CH2, CH3 from alcohol. So this new link is an ester link. The question is structure formula, so let's write down the structure formula. So we will have CH3, 2, CH, COO, CH2, CH3. So that's the structure formula. Next is empirical formula. So let's write the molecular formula first. So if we add all the carbon together, we will have 6 carbon, so C6H12O2, and we can simplify it. So we will have C3H6O.